Just look at this vertical landing. Smooth, impressive. No catapults, no arrestor wires. This is the F-35B. So, why is the U.S. Navy struggling so much with the electromagnetic catapults on the USS Gerald R Ford aircraft carrier? Why not simply abandon everything and use the F-35B? It takes off vertically. It's simple. It's economical. On the surface, this seems like an absolute stroke of genius, and the rest of the world is doing it. Cross the Atlantic, and you'll see the Royal Navy. They've bet their entire fleet on the F-35B. The HMS Queen Elizabeth, a 65,000-ton ship, operates without nuclear reactors, without catapults, without arrestor wires, just a ski jump at the bow. Simple, effective. Or consider our own fleet, the USS Tripoli, an amphibious assault ship transformed into a light aircraft carrier. The F-35B works perfectly there. So, why does the $13 billion supercarrier USS Gerald R Ford reject this option? Why does the most powerful ship on the planet turn away the most versatile aircraft, an aircraft adored by both the British and the U.S. Marines? The answer isn't politics, nor is it arrogance. It's a matter of pure geometry. Welcome to Border Watch Daily, where we dissect the technological and strategic paradoxes shaping our world. Let's examine the cross-section of the F-35B. To hover, it must house a massive lift fan directly behind the cockpit. To an engineer, this fan isn't a miracle. It's a gaping void. It consumes space vital for two critical elements at sea: fuel and firepower. This fan obstructs the internal weapon base, robbing you of space for heavy anti-ship munitions, approximately 900 kilograms each. You're forced to trade invaluable stealth for external ordnance. In cruise flight, this fan is just a dead mass of metal. It doesn't help you extend your range. It fundamentally weakens its combat capability. The British accept this compromise because their doctrine is to defend European coastlines. But for the U.S. Navy, putting the F-35B on the Ford would transform a nuclear fortress designed for ocean dominance into a mere coastal helicopter platform. It's akin to powering a toaster with a nuclear reactor. This brings us to the stark reality of the Lightning II family. The F-35A has become the standard for global air forces. The F-35B has ushered in a new era for smaller fleets and amphibious ships. The F-35C, however, is an exclusive anomaly. It's not designed for the masses. It is operated solely by the U.S. Navy on the most powerful supercarriers in history. Why? Because it's the only variant that eliminates that cursed lift fan, allowing it to carry significantly more fuel. It's the only variant with wings large enough to truly dominate the vast expanse of the Pacific. But here lies the true irony of physics. The Ford was conceived solely to support the F-35C's unique capabilities, and the F-35C was designed exclusively to operate from the Ford. Yet, today, they cannot meet. Observe the Ford's deck today. It's empty. No F-35C in sight. The world's most modern ship is rejecting the world's most modern weapon. Why? Because this aircraft operates at temperatures 370 degrees Celsius hotter than the ship can withstand. Because it is louder than the limits of human survival. And because it demands capabilities that the engineers designing this ship in 2005 couldn't have even imagined. We built a cage in 2005 for a monster of 2025, and now the cage is cracking. Stick around as we're about to reveal why a fundamental physics error on a 100,000-ton vessel created a $13 billion paradox. How do you correct a physics error on 100,000 tons of steel floating in the middle of the ocean? Welcome to the synchronization gap. We agree the F-35C is indispensable. There is simply no alternative. So, why was the Ford, the most modern ship, delivered without being ready for it? Many view this as poor planning. I call it the cruelty of materials science. Consider the shipbuilding process. When you lay the keel of a 100,000-ton ship in dry dock, you commit in concrete and steel. When two 5-centimeter thick steel plates are welded, there's no Control-Z function. You can't download a software update to change the diameter of a water pipe or the location of a load-bearing bulkhead. This is a concept engineers refer to as the frozen base. Let's rewind to 25. This was the year the U.S. Navy locked in the Ford's hull design. At that time, engineers had to make crucial decisions. Where would the cables run? How large should the cooling pipes be? How powerful a generator would be needed? The problem. In 2005, the F-35C was a little more than a promise. It existed only on CAD drawings. It hadn't even flown yet. The most critical documents, called ICDS, Interface Control Documents, governing weight, exhaust gas temperature, and power requirements, were still fluid. The Navy fell into a strategic trap known as concurrency. They applied a design-build strategy, construct the hull, the ship itself, while awaiting the completion of its critical guts, the aircraft, radar, and catapults. This was a colossal industrial gamble. They bet everything on the fact that once the ship was completed, the aircraft would be too, and that the two puzzle pieces would fit together perfectly. They lost that gamble. The CVN 7-8 progressed faster than the aircraft. It was born before the F-35C's final technical requirements were even locked in. The physical differences of the completed C variant came as a shock. The F-35C is not a repackaged FA-18. It's an entirely different beast. Let's begin with the F-35C's first brutal contact with the deck. The Navy calls it a controlled flight into terrain, landing, a term that sounds gentle. But physically, it's a controlled crash. Pilots don't flare the nose to glide in, like with older jets. Instead, they fly a 30-ton aircraft directly onto the steel deck. The 2005 hull structure was never designed for the sheer frequency of this violent surgical impact. And the moment it stops, a logistical nightmare begins. Its massive foldable wings consume vital deck space, forcing flight deck crews to completely rewrite the entire aircraft movement ballet that has been honed over 50 years. But all these physical pressures pale in comparison to the invisible burden it carries. Data. The F-35C is essentially a flying server wrapped in a stealth shell. It doesn't just drink JP-5 fuel, it ravenously hungers for information. Before its engine can even roar, it must ingest terabytes of mission data, threat maps, and real-time encryption keys. The fiber optic infrastructure and server rooms of the 2005 design simply lacked the bandwidth to feed this digital monster. It's like trying to run a 4K game on a 1990s internet connection. The result is a critical synchronization gap. The CVN 7-8 was delivered with what amounts to an outdated operating system. To operate the F-35C, the ship is forced to return to the shipyard in 2025 for a massive upgrade known as PIA, Planned Incremental Availability. Make no mistake, this is no routine maintenance. It's painful orthopedic surgery, aiming to cut out old steel and transplant a new nervous system. They say the Ford is the strongest cage on the planet. But the problem is, the monster we've locked inside generates a fire hotter than the hell the cage was designed to withstand. The war between steel and fire begins here. Welcome to the toughest test of all, the thermal module. Don't just see the F-35C as another aircraft. From a thermodynamic perspective, it's an industrial blowtorch with wings. The older F, A-18, had 2 engines, distributing the heat, making it manageable. But the F-35C channels its colossal 19,500 kilograms of thrust into a single nozzle. When the pilot engages afterburner, exhaust gas temperatures skyrocket to 1,982 degrees Celsius. Recall your metallurgy. Steel doesn't need to melt to yield. At 538 degrees Celsius, steel begins to lose its hardness. At 1,093 degrees Celsius, it becomes soft as clay. With the F-35C's 1,982 degrees Celsius blast, the problem isn't that the deck disappears, but that it permanently deforms under the 30-ton weight of the aircraft itself. You can't launch a jet from a deck that ripples like a potato chip. If you place an F-35C on an older steam catapult, when the pilot throttles up, the blast deflector behind it won't just heat up. The passive steel side panels will turn into candle wax. They will deform, bend, and lose structural integrity before the aircraft even leaves the ground. The Navy's solution wasn't simply to add more steel. They had to modify the ship's entire circulatory system. Engineers had to perform surgery on each deflector, inserting a copper-nickel alloy vascular system. They pump cold seawater directly from the ocean into the heart of the panels to absorb this thermonuclear rage. But fire isn't the only destructive force at play. Look at your feet. The traditional epoxy-based anti-skid coating, which served us for 50 years, has simply capitulated. Faced with the F-35's thermal shock, it doesn't melt, it explodes. This phenomenon is called spalling. The deck surface detaches in sharp pieces, turning into dangerous shards, ready to be sucked into a $100 million engine. It's time to abandon the paint mentality and adopt an armor mentality. Chemical epoxy is obsolete. Against the F-35's heat, it evaporates like water. The new solution is twin-wire arc spraying. Engineers use high voltage to melt aluminum and ceramic wires, then project them onto the deck with high-speed air. Upon impact, they don't stick like glue. They mechanically bond to the steel at a microscopic level. The result is a ceramic metal skin, the only thing strong enough to withstand a dragon's breath. But even if the deck doesn't melt, the pilot faces a different kind of peril. During initial test launches with the EMAL's electromagnetic system, F-35C pilots reported a terrifying phenomenon: the bobble. As the shuttle pulled the jet, the nose pitched violently upwards and downwards. This wasn't a bug, it was a pure case of resonance. The catapult's pull accidentally, yet perfectly, matched the natural frequency of the nose landing gear's shock absorber. The result: the pilot's head was shaken like a rag doll. They couldn't read critical data on their helmet-mounted display. During the 2 most critical seconds of takeoff, they were effectively blind. The Navy faced a choice: redesign the landing gear, a 5-year endeavor, or find another solution. They chose code. This is the true beauty of the electromagnetic catapult. It's not a dumb steam piston that only knows on or off. It's a precise robot. Engineers rewrote the algorithm, instructing the catapult to pull more gently during the initial milliseconds, effectively breaking the resonance rhythm. The nose stopped shaking, a physics problem solved by software. And when the aircraft leaves the launcher, it leaves a final devastating salute, a sound frequency beyond biological tolerance. It's not just noise, it's a death sentence for hearing. Without proper protection, the crew would never hear anything again. The F-135 engine noise reaches a staggering 150 decibels. At this energy level, sound is no longer an airwave. It becomes a physical weapon. Even if you cover your ears, the sound wave travels by bone conduction, bypassing your ear canal and going directly to the brain, permanently destroying hearing. To survive next to this monster, we need a helmet from the future, the HGU 99P. It doesn't just block noise, it integrates sound pass-through technology. Microchips inside the helmet filter out the jet engine's high-frequency whine, but allow the human voice frequency to pass through. You can stand next to a roaring engine and still hear your teammate whisper. The heat that melts steel, the vibrations that cause blindness, the sound that destroys bones. These aren't design flaws. They are the inherent price of power. And the Ford pays this price with every weld, every line of code, and every processing chip. After all this thermal destruction, neck-breaking vibrations, and ear-shattering noise, the coldest question finally emerges. Is it all worth it? Why is the U.S. Navy willing to spend billions to essentially eviscerate its newest ship just to accommodate the F-35C? Why not continue to rely on the FA-18 Super Hornet formations, a reliable aircraft that performs admirably, or simply use the F-35B to bypass all catapult issues? The answer isn't about prestige, it's about the tyranny of distance. Let's revisit the F-35B. We discussed how its lift fan consumes fuel space, but on a tactical map, what does that truly mean? The F-35B has a combat radius of approximately 1,542 5 kilometers. The F-35C, by removing that fan and having giant fuel-filled wings, achieves a radius of over 2,057 to 5 kilometers, a difference of 514.8 kilometers. For a civilian, that's just a number. For a fleet admiral, it defines the life or death zone. These 514.8 additional kilometers allow the carrier to position itself safely outside the range of enemy anti-ship ballistic missiles, while still launching devastating attacks. If you use the F-35B, you're forced to sail a $13 billion ship directly into the kill zone just so the aircraft can reach its target. That's strategic suicide. So, what about the FA-18 Super Hornet? Why can't it do the job alone? The FA-18 is indeed a fantastic aircraft. It carries a lot of armament, but in the era of modern warfare, it's essentially a bomb truck. It's not stealthy. On the radar screens of advanced S-400 air defense systems, a fully loaded F-A-18 lights up like a Christmas tree. It would be shot down before the pilot even sees the target. This is where the F-35C steps in to save the FA-18 formation. The F-35C doesn't replace the FA-18. It directs it. It plays the role of the quarterback. Thanks to its stealth, the F-35C flies first, penetrating dense air defense networks like a phantom. It doesn't necessarily need to pull the trigger. It collects data, redraws the battlefield map in real time, and transmits target coordinates to the F-A-18S, those bomb trucks, which fly safely in the rear to launch long-range missiles. Without the F-35C as a scout, the F-A-18 fleet is blind. And the final piece of this complex puzzle, control. When the F-35C carries its full internal fuel and weapons for stealth, it's a 30-ton beast. Using an old steam catapult to launch it is an act of brutality. Steam is powerful, but it's dumb. It hits the airframe with a violent, jarring shock, reducing the lifespan of your $100 million composite jet with each launch. That's why the Navy bet everything on emails. Is it perfect? No. It has been a maintenance nightmare. It breaks down more often than the older steam pistons, but it offers something steam can never provide: precision. Steam can only launch heavy fighters. It cannot launch the light and fragile surveillance drones of the future without tearing them apart. Emails can. It can adjust the force to launch a feather or scale it up to launch a tank. It's a technology still maturing, still struggling, but it's the only way to launch the heavy F-35C gently enough for it to last, and the only bridge to the future of unmanned warfare. We are exchanging the reliability of the past for the indispensable capability of tomorrow. Without the F-35C, the USS Gerald R. Ford is merely the world's most expensive floating airport, operating with yesterday's technology. But with the F-35C, it transforms into something else entirely. It becomes the physical embodiment of the ultimate U.S. Navy doctrine: high seas dominance. Think about it. The F-35A is sold to air forces worldwide. The F-35B is shared with the Marines and our closest allies like the United Kingdom and Japan. But the F-35C is the crown jewel. It is exclusive. It belongs to the U.S. Navy alone. No other nation, friend or foe, can replicate this specific combination. A stealth fighter with a combat radius of 2,057, 5 kilometers, launched from a nuclear-powered fortress capable of staying at sea for 50 years without refueling. This grants America an unparalleled capability: the power to deploy an invisible air force to the doorstep of any adversary anywhere on Earth without asking for permission. This is the ultimate, unrivaled advantage. That's why this ship times must times be fixed. That's why we accept the pain of the synchronization gap. Because in tomorrow's war, the winner isn't just the one with the biggest fleet. It's the one who truly masters the horizon. Most people would have tuned out at the word thermodynamics. If you're still here, this video is for you. If this exploration of complex machinery fascinates you, consider subscribing to Border Watch Daily for more in-depth analyses. And now, look again at the empty deck of the USS Gerald R Ford. Many call this gap a waste. Many label it a $13 billion failure. But I don't see a failure. I see courage. The truth is, progress is never a straight line. Progress is a road strewn with blood, sweat, and burnt welds. We cannot stay in an air-conditioned room drawing a perfect future on paper. We must go to sea. We must make mistakes, and we must correct them. The Ford is the pioneer. It accepted to sail with flaws. It accepted to let engineers dissect its steel body. It accepted to withstand 1,093 degrees Celsius of heat. It accepted bone-shattering vibrations. It accepted being pierced, cut, and transfused. Why? So that its successor, the USS John F. Kennedy, CVN-79, doesn't have to endure these same pains. The Kennedy will host the F-35C from day one. It will be perfect, but this perfection is built upon the Ford's scars. It's a silent sacrifice of machinery. The challenges of heat, vibrations, data, all have been overcome. not by the empty promises of politicians, but by the burnt hands of welders, by the cold, calculating minds of engineers, and by the unwavering will of the U.S. Navy. Ultimately, this story isn't just about aircraft or ships. It's about the very philosophy of power. The strong are not those who never make mistakes. The strong are those who dare to look a physics error in the face and use their intellect to bend it to their will. That is how we conquer the ocean.